All right, welcome back to the deep dive. Today, we are plunging headfirst into a topic that is, well, absolutely fundamental if you're building modern systems or prepping for a technical interview. How do you handle transactions, those critical all-or-nothing operations, when you're not in the cozy world of a single database, but spread across multiple microservices? It gets tricky, fast. Our goal here is to really untangle this complexity so you can talk about it confidently, design systems better, and, nail those interview questions.
That's a great way to frame it. Moving from a monolith where, let's face it, the database just handles transaction boundaries for you.
Yeah.
Well, moving to microservices where your data is scattered, it fundamentally changes everything about how you think about consistency.
Yeah.
Mastering this isn't just academic, it's a core skill for senior engineers. Getting this right and explaining it clearly is really a key differentiator.
Okay, so let's rewind just a second and establish our baseline. When we say transaction in computing, especially related to data, what are we actually talking about? What's the core idea there?
At its most basic, a transaction is a set of operations that must be treated as a single logical unit. Like, think of transferring money between bank accounts.
Okay.
You deduct from one, you add to another. You absolutely need both steps to happen, or neither. If something fails after the deduction but before the addition, well, you're in a really bad state.
Right. Money just vanishes or appears from nowhere.
Exactly. So a transaction ensures it's all or nothing. If something goes wrong midway, the system should revert everything back to the state it was in before the transaction even started, like it never happened.
Right, the classic all or nothing. And for single databases, we have this golden standard, the ACD properties, atomicity, consistency, isolation, durability. Can you give us the quick rundown on what those mean and why they're so powerful when everything's in one place?
Absolutely. Yeah, ACD is sort of the bedrock guarantee that a reliable database provides for its transactions. Let's break it down. Atomicity. This is your all or nothing, just like we said. If any part of the transaction fails, the entire sequence is rolled back. It's like a single light switch. Either the whole circuit is on or it's off. No flickering in between.
Got it. All or nothing.
Consistency. This means a transaction takes the database from one valid state to another valid state. So it respects all your defined rules and constraints. You don't end up with, data that violates your schema or your business rules. It keeps things sensible.
Keeps the data making sense.
Okay. Isolation. This is all about concurrency. If you have multiple transactions happening at the same time, isolation ensures they don't step on each other's toes. So one transaction's intermediate, sort of half-finished work isn't visible to others until it's fully committed.
Like people editing different parts of a Google Doc at the same time. You don't see their half-typed sentences until they're done.
Exactly like that. You only see their final changes, not the messy drafts. Keeps things clean. And finally, durability. Once a transaction successfully completes and is committed, those changes are permanent. They're written to persistent storage, like a hard drive, and will survive system restarts, power outages, things like that. It sticks.
That makes a lot of sense. So if we're back in our monolithic MusiCorp example, single database, doing something like updating customer 2, 3, 4, 6's status in one table and removing their pending enrollment from another table. That's just one database transaction, right?
Precisely. That single transaction boundary wraps neatly around both the customer status update and the enrollment record deletion. The database itself guarantees the ACD properties for both operations together.
So it guarantees atomicity.
Yep, either both happen or neither. And it ensures consistency across those related pieces of data within its single domain. That's the immense value of having everything under one roof with a single ACD guarantor. Makes life simpler in that respect.
Okay, here's where the plot twist comes for microservices. You take that monolith, you break it apart. Now, the customer service owns customer data in its database, and maybe the enrollment service owns enrollment data in its database. Separate databases.
Exactly. And suddenly the same business operation verifying customer 2, 3, 4, 6 and cleaning up their enrollment, it's no longer a single transaction spanning tables in one database. It's now a process that likely involves a local transaction in the customer services database and a separate local transaction in the enrollment services database.
And the problem is those two local transactions are independent. They don't know about each other, really. The customer service might successfully update the status, commit that change, but then it's called to the enrollment service, maybe it fails. Or the enrollment service itself has an issue with its own database operation.
Right. Bingo. Now you've potentially got customer 2346 marked as verified in one service's database, but their pending enrollment record is still sitting there untouched in another service's database.
Ugh, inconsistent state.
Exactly. You've lost that fundamental atomicity across the entire business operation. You're in an inconsistent state across your distributed system. And this is the core challenge of distributed transaction management. How do you maintain consistency when your data and the operations on it are scattered?
Yeah.
It immediately throws you into the world of trade-offs, often discussed with things like the CAP theorem, where achieving immediate strong consistency across network partitions, well, it often comes at the cost of availability.
Okay, so given that challenge, the first thought for many people, especially if they're coming from that comfortable monolithic world, is, okay, can't we just make a transaction that somehow spans these multiple databases, like stretch it across?
Yeah, that's a very natural thought.
And this often leads people to look at distributed transaction protocols. And the classic example everyone mentions is two-phase commit, or 2PC.
Right, 2PC. It's one of the, let's say, earlier attempts to tackle this exact problem. It aims to bring that acity-like atomicity back, or at least simulate it in a distributed setting. It involves a central coordinator, think of it as the orchestrator, and multiple participants, sometimes called workers, like in our example, worker A managing the customer database and worker B managing the enrollments database.
Okay, so how does 2PC try to make this work? How does it coordinate things?
Well, it does it in two distinct phases, hence the name two-phase commit. Phase one is the prepare or voting phase. The coordinator kicks things off. It sends a prepare request to every participant involved in the transaction. It's basically asking, are you ready to perform the required operation? And crucially, can you guarantee that you'll be able to commit it later if I tell you to?
Okay.
So for customer 2346, the coordinator asks worker A, can you update the status and guarantee you can commit? And it asks worker B, can you delete the enrollment record and guarantee you can commit?
That guarantee part sounds important. But also maybe where the trouble starts. How do the workers actually make that guarantee?
Ah, yes. This is where the significant drawbacks often creep in. To make that guarantee, participants typically have to do two things. First, they usually write the intended change to some kind of stable log, like a write-ahead log.
Yeah.
Second, and this is the big one, they have to acquire locks on the resources they need to modify.
Locks
Yeah.
across services.
Yes. Worker A locks the specific customer row it needs to update. Worker B locks the enrollment row it needs to delete. These locks prevent any other transaction, whether local or another distributed one, from changing that data until this whole 2PC process is finished.
That sounds like it could block things up quite a bit.
It absolutely can. We'll get more into that. So if all the participants successfully prepare, meaning they acquire their locks and log their intent, and they all respond, yes, I'm ready and lock, then we move to phase two. But if any participant says no, maybe because it can't get a lock or encounters an error, or if it simply fails to respond within a timeout, the coordinator immediately sends a rollback or abort command to everyone. All participants then discard any temporary changes and, importantly, release their locks.
Okay, so it's unanimous agreement or nothing in phase one. What happens in phase two if everyone did vote yes?
Phase two is the commit phase. If and only if the coordinator received that yes vote from all participants in phase one, it makes the final decision. Commit. It then broadcasts a commit command to every single participant.
And they just do it.
Yep. Upon receiving the commit command, each worker makes the changes permanent. They apply the update or deletion they prepared in phase one, and then they finally release the locks they were holding.
That whole process, especially the locking across different services, waiting for network calls, waiting for everyone to respond, it sounds like it could be incredibly slow and maybe fragile.
It absolutely is, on both counts. Managing distributed locks is inherently complex. You run into issues like deadlocks, where service A is waiting for a lock held by B, and B is waiting for a lock held by A, and these are much, much harder to detect and resolve across services than within a single database process.
Yeah, I can imagine.
And the latency. The longer any part of the network takes, or any participant takes to respond, the longer those crucial database resources are locked up. This directly impacts the throughput and the availability of your entire system. Holding locks for potentially seconds across network boundaries, that's often a deal breaker for performance.
So using 2PC for anything that takes more than a tiny fraction of a second sounds like a bad idea.
Generally, yes. It's often considered a major anti-pattern in microservices for anything but extremely short, simple operations. The performance hit is usually too high.
And what about failures during the process itself? You mentioned participants failing to respond in phase one. What if, say, a worker votes yes in phase one, locks its resource, but then it crashes before it receives the command from the coordinator in phase two?
That's a critical failure scenario, and it really highlights the fragility of 2PC. If a worker crashes after successfully preparing but before committing, it's left in what's called an in-doubt state. It doesn't know whether the final decision was commit or abort.
And its locks?
Its resources remain locked, potentially indefinitely blocking other operations, unless you have a really complex recovery process. This often involves the coordinator querying the worker when it comes back online, or sometimes even requires manual intervention by an operator to figure out the state and release the locks or force a commit to roll back. It's messy.
Ouch. And what if the coordinator itself fails?
Even worse, potentially. Especially if the coordinator fails during phase two after it has sent commit to some workers but not others. Now you have some workers who have committed the transaction permanently and others who are still waiting or crashed before receiving commit. This leads to a definite data inconsistency across your system, one that might be very difficult to resolve automatically.
So assuming the coordinator is infallible is a bad assumption.
It's a major anti-pattern you see when people try to apply 2PC naively without considering these failure modes deeply. The coordinator is often a single point of failure unless made highly available, which adds more complexity. And this brings us right into interview territory, because these nuances are exactly what interviewers probe for. A very common question is something like, explain the two-phase commit protocol and discuss its suitability, or lack thereof, for microservices.
Okay, so let's say you get that question. How should someone approach answering it to sound knowledgeable?
Well, first, you need to show you understand the mechanics. Clearly describe the two phases, prepare vote, then commit abort. Explain the roles of the coordinator and the participants, workers. Definitely mention the locking mechanism in phase one and the final commit or rollback in phase two. Show you get how it attempts to achieve atomicity.
But then pivot.
But, and this is the crucial part for the microservice context, you absolutely must immediately pivot to explaining why it's generally not suitable for typical microservice use cases. You have to highlight the significant drawbacks we just discussed.
Okay, so what are the absolute biggest red flags or anti-patterns a candidate might reveal when talking about 2PC in an interview? Things that make the interviewer think, I don't quite get it.
One of the biggest is definitely overlooking or seriously downplaying the performance impact. If you talk about 2PC and don't immediately bring up the latency issues, the blocking nature of those distributed locks, and the hit to throughput and scalability, that's a huge red flag.
Right, ignoring the practical cost.
Exactly. Another is not discussing the failure modes adequately. Failing to mention the in-doubt state, the problems with coordinator failure, and how difficult recovery can be suggests a superficial understanding. And maybe the most fundamental red flag is treating distributed transactions like they're just slightly slower versions of local database transactions.
Because they're fundamentally different?
They are fundamentally different, especially in their guarantees around atomicity in the face of partial failures and their failure characteristics. Pretending they're the same beast is a dangerous oversimplification.
So the fact that distributed systems, they will have network glitches, services will temporarily go down, that inherent unreliability makes 2PC a really problematic fit.
Precisely. You have to design distributed systems assuming failure is not the exception, but a normal occurrence. 2PC, it kind of assumes relatively reliable communication and stable participants to work smoothly, which often isn't the reality in a large, dynamic microservice environment. It heavily prioritizes consistency during the transaction window, often at the expense of availability, which frequently conflicts with the resilience and scalability goals of microservices.
Okay, so if 2PC has all these serious drawbacks, what are people actually using? What are the more common patterns for managing consistency across microservices in the real world?
Yeah, good question. Most modern microservice architectures really lean towards patterns that, let's say, accept eventual consistency rather than trying to force immediate strong consistency across service boundaries using protocols like 2PC.
Eventual consistency, meaning things might be out of sync for a short while, but they'll get fixed up eventually.
That's the core idea, and the most common pattern you'll see implementing this is the Saga pattern.
The Saga pattern. Okay, I've heard of that. How does that work differently from 2PC?
It's a fundamentally different approach. Instead of one big atomic distributed transaction holding locks everywhere, a Saga breaks the overall business operation down into a sequence of smaller, independent, local transactions. Each local transaction happens entirely within a single participating service.
Okay, so like inventory deducts its stock, local transaction 1, then maybe tells payment to charge the card, local transaction 2.
Exactly. The key difference is what happens if something goes wrong. If one of these later local transactions fails, say, the payment fails, the Saga doesn't try to roll back the whole thing in the 2PC sense. Instead, it coordinates a series of compensating actions.
Compensating actions, like undo operations.
Precisely. Think of it like a long business process with an undo button defined for each step that succeeded before the failure. If step 3, payment, fails, the Saga orchestrator triggers a compensating action for step 1, inventory, maybe telling inventory to add the stock back. So you undo the work of the preceding successful local transactions.
Okay. So you avoid holding those long-lived distributed locks.
Exactly. That's the huge benefit. You avoid holding locks across services for the entire duration of the business process. This vastly improves availability and performance compared to 2PC. Now, coordinating these sagas often involves using event-driven architectures.
How so?
Well, when one service completes its local transaction, like inventory deducting stock, it might publish an event, say, order inventory reserved. Another service, like payment, subscribes to that event and gets triggered to perform its part of the saga.
And you need to make sure that event gets published reliably, right?
Absolutely critical. You can't have the database commit succeed, but the event publishing fail. This is where patterns like the outbox pattern come in. You essentially write the event to a special table within the same local database transaction that modified the business data. Then, a separate process reliably reads from that outbox table and publishes the events. This guarantees atomicity between the state change and the event publication.
Clever.
And one more crucial piece for sagas, especially in event-driven systems, is idempotency.
Idempotency, meaning doing something multiple times has the same result as doing it once.
You got it. Because in distributed systems, messages or events can sometimes be delivered more than once due to network issues or retries. So the service handling the event, like the payment service processing a process payment command, needs to be designed so that if it accidentally receives and processes the same command twice, it doesn't, for example, charge the customer twice. It needs to recognize it's already done that work and just acknowledge it.
So Saga gives you better performance and availability, avoids those nasty distributed locks, but the trade-off is that you might have a brief window where the system is temporarily inconsistent across services. Like, inventory is deducted, but payment isn't processed yet.
Precisely. You embrace eventual consistency, the system will become consistent, just not necessarily instantaneously across all services involved in the operation. This aligns much, much better with the reality of distributed systems operating over unreliable networks.
And this is generally preferred over 2PC.
Overwhelmingly so for most typical business operations and microservices. While some very specialized high-end distributed databases like Google Spanner do achieve distributed ACD transactions, they do it with incredibly complex and expensive specialized infrastructure and tight operational controls. That's not something most application development teams can or should try to replicate for their standard microservice interactions. For most of us, Saga and event-driven patterns are the de facto standard for managing workflows across services.
And that makes a lot of sense. It seems pretty clear why Saga is usually the better fit.
Yeah.
But just to be thorough, when would you ever seriously consider using 2PC in a modern microservice system? Is there any place for it?
Okay, fair question. You might consider 2PC in extremely narrow, very specific circumstances. Think scenarios where all of these conditions apply. 1, the transaction needs to be incredibly short-lived. We're talking milliseconds, truly, not seconds or minutes. 2, the number of participating services must be small, like maybe 2 or 3, and relatively stable, not something that changes often. 3, you need absolute, immediate, strong consistency across those few tightly coupled resources, and that consistency is paramount, more important than temporary dips in availability or performance hits. And 4, you have the operational maturity and tooling to handle the complex failure modes and recovery scenarios robustly.
So it's a very niche use case.
Extremely niche. Maybe for something like ensuring a unique username is claimed across 2 critical, closely linked identity systems simultaneously, and the operation is lightning fast. But for almost everything else involving business processes, spanning multiple services like orders, enrollments, workflows, Saga is going to be the much more pragmatic and resilient choice. Which leads nicely to another potential interview question. When would you choose the Saga pattern over two-phase commit?
Okay, and the answer there seems to be focus on the trade-offs again.
Exactly. You explained that Saga is the go-to for longer-running business operations, anything involving more than a couple of services, or situations where availability and scalability are key. Why? Because it avoids distributed locks. You mentioned that the complexity shifts from managing locks and coordinator failures to designing good compensating actions and ensuring reliable, idempotent message handling.
And contrast that with 2PC.
Right. Then you contrast it with 2PC, saying it's only potentially suitable for those very rare, extremely short critical transactions where that immediate, strong consistency is an absolute must-have, and you're willing to pay the significant price in terms of performance, availability, and operational complexity. Showing you understand why you'd choose one over the other based on these trade-offs is key.
Got it. Let's try a quick scenario then. Imagine you're in a system design interview. The interviewer sets up the scene. A user places an order on an e-commerce site. This action needs to deduct inventory, which is handled by the inventory service, and it also needs to process the payment, handled by the payment service. How would you approach explaining the transaction management strategy here? And crucially, what clarifying questions would you ask the interviewer first?
Okay, great scenario, super common. First thing, I would not jump straight to proposing a solution like Saga or, heaven forbid, 2PC.
Okay, what would you do first?
I'd start by framing the core problem that the microservice architecture introduces. Something like, okay, interesting problem. In a monolithic system with a single database, this would be straightforward, wrap the inventory deduction and payment recording in a single AC transaction. But here we have two separate services, likely with their own databases. So the main challenge is we've lost that automatic atomicity across the entire order process. We need a strategy to manage consistency between the inventory and payment services.
Setting the stage, then questions.
Then absolutely launch into clarifying questions. This shows you're thinking critically about the requirements before designing. I'd ask things like, what's the required consistency level for this operation? Is it acceptable if inventory is reserved for a brief period before the payment is confirmed? Or does it need to appear atomic to the user? How long do these individual operations deducting inventory, calling the payment gateway, typically take? Are we talking milliseconds or potentially seconds? What's the expected transaction volume or load on this ordering process? Crucially, what are the business consequences if the payment fails after inventory has already been reserved or deducted? How critical is it to unreserve that inventory immediately? Is the payment service interacting with an external third-party gateway? Because those often have higher latency and failure rates.
Excellent questions. They really dig into the practical constraints.
Yeah,
Asking those demonstrates a much deeper level of understanding than just blurting out Saga.
exactly. You need to understand the context.
So let's say you get some answers. Maybe they say eventual consistency is acceptable, payment can sometimes take a few seconds, volume is high, and failed payments should release inventory reliably, but not necessarily instantaneously. Based on that, what patterns would you then discuss?
Okay, based on those answers, especially the acceptance of eventual consistency and the potentially longer duration of payment processing 2PC is immediately off the table. I would strongly recommend the Saga pattern as the most appropriate and robust approach.
Perfect. So you're showing you understand the problem, you ask the right questions. To tailor the solution, you recommend the most suitable pattern, Saga, and you can actually discuss its implementation details like compensating actions, reliable messaging via outbox, and idempotency. That's a strong answer. Now, what if? What if you're in the middle of explaining something complex like this, maybe the nuances of Saga choreography versus orchestration, and you realize you misspoke slightly? Or maybe you could have explained a concept a bit more clearly. How do you recover gracefully in an interview?
Oh, it definitely happens. Everyone misspeaks occasionally, especially under pressure. Don't panic. The best approach is to correct yourself calmly and clearly. Acknowledge the slip-up, make the correction, and if possible, briefly explain why the correction is important.
Can you give an example?
Sure. Let's say you were explaining to BC and you accidentally implied it was okay for moderately long transactions. You could say, actually, let me refine that point about 2PC's applicability. I might have implied it could handle moderately long operations, but I need to stress that its blocking nature really makes it impractical for anything beyond truly short and millisecond level transactions due to the severe performance impact of holding those distributed locks. For anything longer, patterns like Saga are definitely the way to go.
Ah, okay. So you just own it, fix it, and maybe add a little extra context.
Exactly. Correcting yourself shows self-awareness, critical thinking, and actually reinforces your understanding of the nuances. It's much better than letting a mistake hang in the air or trying to bluff your way through it. Interviewers generally appreciate honesty and clarity.
Okay, so maybe let's quickly summarize the key takeaways from our deep dive today on distributed transactions and microservices. What should you really remember? First, monoliths give you that nice, simple ACID transaction management within a single database boundary. Life is easier there, consistency-wise. But microservices break that boundary.
Right. Microservices inherently break that single boundary. This leads to the loss of automatic atomicity across business operations that span multiple services, forcing you to deal with distributed data consistency challenges. Second, two-phase commit, 2PC, is a protocol that tries to bring atomicity to distributed systems, but, and this is a big but it generally suffers from significant performance issues due to locking, it has complex failure modes, like that in doubt state, and it reduces availability. This makes it generally unsuitable for common microservice scenarios. Remember, it heavily prioritizes consistency over availability.
And understanding those trade-offs is vital.
Absolutely vital. Think CIP theorem: consistency, availability, partition tolerance. You often can't have all three perfectly, especially immediate consistency and high availability in the face of network partitions. You need to understand what you're optimizing for. Fourth, look to the alternatives. Patterns like the Saga pattern, combined with event-driven architectures, often using the outbox pattern for reliability, and techniques like ensuring idempotency in your service operations. These are the preferred, pragmatic approaches in modern systems. They typically embrace eventual consistency to gain better availability, resilience, and performance. The complexity shifts from distributed locking to managing compensating logic and reliable messaging.
Yeah, knowing those distinctions is the core problem, why 2PC is usually the wrong answer for microservices, and what alternatives like Saga actually offer that seems absolutely key for any system design discussion or interview. And understanding why you can't just pretend distributed transactions work like simple local ones, that feels like a major differentiator. Getting that wrong is a big red flag, isn't it?
Yeah, it really is. It signals a lack of understanding about the fundamental challenges of distributed systems. Okay, here's a final, maybe slightly provocative thought to leave you with. Given how incredibly complex and often problematic managing transactions across service boundaries really is, with things like 2PC being largely unsuitable and Sagas requiring careful design of compensating actions, could there be situations where the most pragmatic and robust design choice, even within a broader microservice architecture, is to deliberately keep certain very tightly coupled data and the functionality that absolutely must modify it atomically together?
You mean like a mini monolith within the microservices world?
Kind of, maybe grouping that highly cohesive functionality and its data into a single, slightly larger but still well-defined service boundary, managed by a single database. Sometimes, strategically avoiding the need for a distributed transaction altogether by drawing your service boundaries carefully might be the simplest, most reliable answer to prevent the pain. It's about choosing the right boundaries to minimize that cross-service transactional complexity where possible.
That's a really interesting point. Don't just break everything apart for the sake of it. Think about the transactional boundaries, too. Fantastic. This was a great deep dive into a really challenging but honestly essential topic. Hopefully this helps clarify things and makes you feel much more prepared, whether you're actually designing these systems or just walking into that next interview room.
Yeah, understanding the trade-offs here is absolutely everything. It's not just about, memorizing pattern names like Saga or 2PC. It's about deeply understanding the strengths, the weaknesses, the failure modes, and the why behind choosing one approach over another in a given context.
We'll definitely keep exploring these critical system design concepts in future deep dives. Perhaps we can even do a dedicated session just on the different ways to implement the Saga pattern itself. That sounds useful.
Could be very interesting.
So if this was helpful for you, please do let us know. If you found this deep dive valuable, maybe hit that like button. And definitely subscribe to catch a future deep dives where we unpack complex tech topics just like this one.
Yeah, and we'd love to hear from you.
Absolutely. Leave a comment below. Let us know if you have any questions about distributed transactions, 2PC, Sagas, or if there are other challenging system design concepts you'd like us to tackle next time.
Thanks for tuning in. Until next time.
Thanks for joining us for this deep dive.